Picture the quietest place on Earth, a steel chamber pumped emptier than interstellar space. Walls chilled until the final wisps of gas freeze solid. Turn off every laser, every lamp, every heater. By common sense, the stage should now be blank. No atoms, no light, perfect stillness. Yet when physicists lower a hair-fine microphone, a nanomechanical reed, they hear a faint murmur. The reed trembles, as though prodded by invisible fingertips. This is zero-point energy, the irreducible jitter of quantum fields. Even when we evict all matter and drain all heat, the fields themselves refuse to sit perfectly still. Like children instructed to be quiet at bedtime, they fidget in the dark, wiggling just enough to betray their presence. The electromagnetic field sprouts pairs of virtual photons that appear and vanish quicker than any camera can blink. Electron fields do the same with particle-antiparticle twins. Each flicker is tiny, but across the vast expanse of space, the aggregate hum becomes profound. Why can't the fields simply relax? Because quantum rules forbid absolute precision. Pin them to zero motion, and their energy becomes hopelessly uncertain. Nature chooses the gentler compromise, perpetual, minimal restlessness. It is quiet enough that our bodies feel nothing, yet insistent enough to tilt the weight of an electron. Curve the orbit of hydrogen's lone passenger, and most wondrous shape the destiny of black holes. The stage, it seems, is never empty. It is a restless sea whose surface we mistake for calm night air. In a laboratory lit by the soft glow of oscilloscopes, two mere smooth metal plates stand face to face, separated by less than a human hair. They carry no charge, feel no classical pull, yet over days they creep toward each other with a measurable force strong enough at tiny gaps to snap fragile supports. No hand pushes them, no magnet lures them. The culprit is the restless vacuum itself. Between the plates, only certain electromagnetic ripples can fit, waves whose peaks align neatly with the narrow cavity. Outside, the full orchestra of wavelengths plays without restriction. The mismatch creates a subtle pressure difference. More modes jostle outside than in, so the plates are gently pressed together. This phenomenon, predicted by Dutch physicist Hendrik Casimir in 1948, is today verified with exquisite micro-machined levers. Engineers even harness it, sometimes grudgingly, in nanoscale gears where the Casimir glue can cause parts to stick, or, with clever design, to latch by intent. Visualize children jumping on a trampoline. If two hefty youngsters claim the center, fewer places remain for the others to bounce, so the surrounding crowd presses inward. The plates are those children. The vacuums, ceaseless modes, are the eager jumpers. Remove the plates, and the pressure equalizes. No squeeze. Insert them, and the imbalance reappears, a whispering force born from nothing at all. What feels like a magician's trick is merely quantum bookkeeping. Limit the room for fluctuations, and they push back. Even emptiness has preferences, and metals polished to atomic smoothness. Let us feel that phantom hand. Aim a glass prism towards sunlight, and Newton's tidy rainbow appears. Red, orange, yellow, through violet. Each strip marking a precise energy of light. But when physicists inspected hydrogen's spectrum with wartime radar gear in 1947, one crimson line sat ever so slightly out of place, nudged just a hair from theory. The culprit was not faulty glass. It was the vacuum again, slipping its invisible fingers into the atom. Inside hydrogen, an electron orbits a proton like a lone moon. Classical quantum theory said two particular orbits should share identical energy. Yet Willis Lamb's radiofrequency measurements showed a minuscule gap. The Lamb shift. The restless zero-point photons swarm around the proton. It's momentarily polarizing space, and that tiny storm tugs on the electron's path. A trillionth of a second jitter lifts one orbit higher than the other. By a few parts in a billion, enough for careful ears to hear. Fast forward to today's muon G2 experiment. Muons, heavier cousins of the electron, loop in a magnetic ring. If empty space were truly empty, their magnetic wobble would match in-clean calculations. Instead, vacuum pairs spring into existence, cling to each muon for fleeting instants, and alter its precession. The latest data hinted a wobble beyond standard model expectations. Perhaps the vacuum hosts ripples from fields we have yet to sew into our cosmic quilt. Takeaway: even delicate spectral lines and subatomic compass needles reveal the vacuum's influence. Silent fluctuations leave audible fingerprints on the tiniest scales. Imagine floating in deep space, heater off, stars distant pinpricks. To you, the vacuum feels frigid and empty. Now fire up a rocket pack and accelerate hard. Strangely, a faint warmth seems to bathe your visor, according to physicist Bill Unruh. An accelerating observer perceives the vacuum as a thermal sea. Motion stirs virtual photons into reality, much as whisking cream conjures peaks from liquid smoothness. The faster you accelerate, the hotter the perceived glow, though reaching room temperature would demand unimaginable thrust. Stretch this idea to a cosmic extreme: the edge of a black hole. From afar, the event horizon looks like an inescapable one-way gate. Yet Stephen Hawking realized that quantum fields do not respect such absolutes. One member of a virtual particle pair can fall inward, leaving its twin free to escape as real radiation. To distant eyes, the horizon itself glows, Hawking radiation, ever so faintly, over stupendous timescales. That glow will bleed a black hole dry and returning its locked-away mass to the wider universe as whispers of light. Both effects share a moral. What counts as nothing depends on how you move. Inertia sees calm, acceleration sees heat. Gravity, by bending space-time, can mimic endless acceleration, turning the silence around a black hole into a subtle hiss. Our concept of vacuum is therefore not universal, but perspectival. A reminder that reality is richer than any single vantage point can reveal. Your takeaway: change your motion, or stand near a horizon, and the vacuum itself lights up, proving that emptiness is in the eye and speed of the beholder. Listen closely to a quiet audio recording and you'll notice hiss, the unavoidable static of microphones and electronics. Light carries its own hiss, a jitter born of zero-point energy. For decades, that quantum rustle set the sensitivity floor of the world's finest instruments, till physicists learned to squeeze it. Think of uncertainty as a partly filled water balloon. Press it narrower one way, and it bulges elsewhere. In quantum optics, we do the same with the vacuum's noise. Special crystals, bathed in laser light, reshape the random fluctuations, so that one property of the light, the phase, say, grows calmer, while its partner, the brightness, gets extra jitter. Choose which side matters for your measurement, and the unwanted rumble drops away. The payoff is grand. LIGO, the observatory that hears black holes collide, injects squeezed light into its kilometers-long cavities. The calm phase lets laser beams register mirror motions smaller than a proton's width, turning what was once vacuum static into a sharpened ear for space-time tremors. In superconducting circuits, engineers coax vacuum fluctuations to split into real photon pairs, our microwave echo of the Casimir Effect, feeding quantum computers with tailor-made signals. Future clocks may beat with accuracy limited only by how well we can sculpt vacuum noise. Dark energy detectors now on drawing boards plan to use squeezed states to sniff the universe's faintest pushes. What earlier generations called empty has become pliable raw material, a medium we mold like glass into lenses for the very small and the very distant. Your takeaway? By squeezing the vacuum's built-in jitter, we transform quantum rustle into a precision tool, proving that even silence can be engineered. We began this chapter seeking emptiness and found instead a restless stage, plates that feel ghostly pressure, atoms nudged by unseen hands, horizons that glow if you rush toward them, and clever machines that sculpt the hush into sharper hearing. The vacuum is not a backdrop but a character, forever whispering beneath the louder actors of matter and light. Yet physics offers another revelation. We can create new vacua, tailor-made ground states inside everyday materials. Cool aluminum to a few degrees above absolute zero, and its electrons pair off, birthing a superconductor where electric ripples flow without resistance. Carve carbon into honeycomb sheets and graphene hosts Dirac-like quasi-particles that sprint as if massless. Twist to such sheets to a magic angle and an entirely different set of rules emerges. complete with its own Higgs-like gaps and superconducting phases. These condensed matter landscapes act as miniature universes, each with distinctive fields, particles, and symmetries. Laboratory playgrounds where we can tune the laws at will. They promise technologies from lossless power grids to topological quantum bits. But more importantly, they let us probe questions too extreme or too expensive to test in particle colliders or deep space missions. In the next part of our journey, we will step into these man-made worlds. We'll watch electrons glide friction-free, meet quasi-particles, stranger than any standard model citizen, and learn how emerging fields and solids mirror, and sometimes mock, the grand fields of the cosmos. Your takeaway. If the true vacuum is a restless sea, condensed matter physics invites us to bottle new seas. Pocket universes where the rules of reality can be rewritten and explored.